Today I'll tell you about fully dynamic submodular cover with bounded recourse. This is joint work with Anupam Gupta. Both of us are from CMU. So I better explain to you what these words in the title mean, and best to do so with an example. Suppose I gave you the hitting set problem. I give you a collection of vertices and a collection of subsets of those vertices, and I'd like you to pick the smallest number of vertices such that you hit every subset, like so. But the problem is more interesting, actually. So really, you don't know any of the subsets up front, and instead they're going to arrive and depart one by one. Your task is to maintain a near minimal solution at every time step, and also avoid changing your solution too much from time step to time step. Let's go through an example run. Suppose this subset arrives. Maybe you'll pick this vertex to cover it. Another subset arrives. It's already covered. Another subset arrives. You pick this one, and so on and so forth. And perhaps at some point, this subset departs, and although you're feasible at this point, you decide you'd rather have a cheaper solution and pay the cost to update your solution. So the goal here is to find a good trade-off between the approximation quality at every point in time, and also minimize the number of vertices that we add and remove at every time step. The second quantity, the number of vertices we add and remove, we'll refer to as recourse. So that was the hitting set problem, but let's take a step back and abstract the core features of this problem that we're solving. There is a universe of possible choices. We'll call this like script n. This is the set of vertices we could have picked. A solution consists of a subset of the possible choices. Every subset has a cost associated with it. For us, it's just a number of vertices in that subset. There's a notion of coverage quality associated with every solution. In our example, it's a number of sets that you've hit in this solution. And crucially, this notion of what it means to cover is changing over time. Now, this is our problem. We're solving a min-cost subset selection problem, subject to the constraint that a function f is maximized. Of course, if this is all I told you, this would be completely intractable. So we're going to assume a little bit more. We'll assume that f is monotone, meaning if a subset A is contained in a subset B, then f of B is greater than f of A. In this light, we can rewrite the maximization criterion as f of s equals f of the entire universe. The function is non-negative. And finally, it satisfies a property called submodularity, meaning it has decreasing marginal returns. More formally, a function f is said to be submodular if for any two subsets A and B, and any x outside of both, f of A union x minus f of A is greater than f of B union x minus f of B, meaning x gives more value to A marginally than it does to B. In a picture, my valuation function for cars is said to be submodular if the added utility I get from a new car is greater if I don't already have a lot of cars. So this is our problem. We're solving min over choice of s subset of n, cost of s, such that f of s is maximized. And the function f is monotone non-negative submodular and evolving over time. We'll say what that means more formally in a few slides. Now, we'd like a competitive solution at every point in time with low recourse. So really, in our paper, this is the fully general problem that we'll solve. For this talk, we'll assume that f is integer valued for simplicity and that all the costs are 1, but we handle the general case in our paper. So what is this problem? The offline version, in which f does not change and is static, is known as submodular cover. It was introduced by Woolsey in 1982, and Woolsey showed that the greedy algorithm that repeatedly selects the remaining elements takes the one that gives the largest marginal increase in the value of f. This algorithm gives a log of f of n, where n is the ground set, plus 1 approximation to the optimal solution. This is known to be optimal unless p equals np, so we can't do any better. And in the example of a hitting set, f of n will be equal to n, which is the number of subsets present in the problem. And so this recovers the classic guarantee of the greedy algorithm for the hitting set problem. Let me convince you that submodular cover is extremely expressive. So version 0 of it is the hitting set problem that we've talked about, also known as set cover. But it goes far, far beyond the hitting set problem. For one, it captures the partial version of hitting set, where the requirement is that you not cover all of the edges, but maybe all of the subsets, but maybe just some fraction of the subsets. You can define a capacitated variant in which every vertex can only be used to cover some capacity number of subsets, Frankensteins of these, and the list goes on. And all of these are captured by submodular cover. I won't harp on this too much, but this problem is really used in a huge number of areas to model like a very, very impressive number of applications. And it's really become quite a popular paper template to take a problem, reduce it to submodular cover, then use the greedy algorithm as a black box. So here's a list of papers that do this. And I'll stress that these are a mix of theory papers and practical papers. So if you can port submodular cover to a dynamic setting, you're really porting like any downstream application to a dynamic setting. All right. So in the remainder of my talk, I will first define the dynamic model that we're considering more formally. I'll then say our results, give you the algorithm and the analysis for the special case of hitting set, and then we will conclude. Let's get started. In our model, an adversary is going to add and remove submodular functions to an active set. And our goal will be to constantly maintain a feasible cover for all of the functions that are currently active. So we imagine that we're holding onto this active set, which is this capital G, and the adversary is going to inject and delete functions, like so. Now, at time t, we'd like a solution st for the function capital F, which is the sum of all the functions currently in the active set. When I say S is a solution, I mean that f of st is equal to f of n, i.e. this is the submodular cover constraint for the function big F. Now, because each of these constituent functions is monotone, capital F is maximized if and only if each of the functions is maximized. So this has the effect of requiring the and of all the constraints currently in the active set. I said we want to keep recourse low. Formally, we'll define recourse as the sum over time of the size of the symmetric difference of solutions at successive time steps. Now we'll play this trick. We'll count deletes as free. We'll only count the inserts as costing us recourse. And the reason we can do this is that every time a vertex is deleted, it must have been inserted previously. And so we can just charge the delete to the insert. This will give us amortized bounds, but that's okay. So let's do the example from the beginning of the talk in this framework. In the hitting set problem, each of the constituent constraints that arrives and departs over time is just the indicator function for whether or not we've covered the ith subset. So as I walk through this example, I'll track the relevant quantities, the functions and the recourse down here. So we see that this framework indeed captures the hitting set problem and generalizes it significantly. Without further ado, let me say our results. So in a stock 2017 paper, Anupam and a group of co-authors gave the first order log n competitive order 1 recourse algorithm for the fully dynamic version of the hitting set problem. Now I claim that this is the optimal possible result. Why is it optimal? Well, log n is the best guarantee you could achieve even offline. And any algorithm that solves this problem must pay at least order 1 recourse. Why is this? Well, imagine that all of these subsets arriving over time were completely disjoint. Well, you'd have to pay 1 per subset arrival. There's no getting around this. Unfortunately, this work does not easily generalize to submodular cover, and so one needs some new ideas. As a second note, earlier this year, in previous work of ours at SODA, we gave an optimal algorithm for the online version of submodular cover, where no takebacks are allowed. So once you buy a vertex, you must keep it forever. Now, unfortunately, this type of algorithm really only works in an insert-only version of this problem, and fundamentally breaks when functions can depart the system as well. Furthermore, because the requirement is more stringent that you never take back any decisions, the guarantees that you can achieve are significantly worse than you can get for the fully dynamic setting. And this will be clear once I show our results in the next slide. So here's our main theorem. We show that there is a polytime and furthermore a deterministic algorithm for this formulation of fully dynamic submodular cover, and it achieves two things. Competitive ratio of order log of f of n, and an average recourse bound that is O tilde of the average over time of these constituent constraint functions evaluated at the entire ground set. This tilde is hiding a single log factor that depends on the ratio of the max to min cost in the problem, but we'll ignore it for the purpose of this talk. So I invite you to pause the video and unpack this bound more carefully if you wish. But the important thing to realize is that these bounds are optimal up to the log factor in the recourse. Now, why is that? Well, let's think about what these give in the special case of hitting set. F of n, this capital F, is just the sum of the indicators of the subsets in the system. So this is the number of subsets, which is just n. On the other hand, this little ft is just an indicator. So evaluated the entire ground set, it's 1. Summed over time, this is t. Divided by t, this is 1. So in this case of hitting set, we recover the bound from the stock 2017 paper up to the tilde here in the recourse. In this talk, we'll prove this theorem for the special case of hitting set and for the case where all the costs are 1. I'll just note that in the full paper, not only do we prove this for the general submodular cover problem, but we also show how to remove the log for a structured class of instances that includes hitting set. So we indeed recover the actual guarantee from the stock 2017 paper. All right, let me give you the algorithm. So if I give you this problem, one thing you might try is to run the greedy algorithm at every point in time. What is the greedy algorithm? Let's define SE to be the subsets hit by E, or the subsets containing the element E. The greedy algorithm repeats for I equals 1 to n the following. Given what it's taken so far, it picks the element that hits the most number of new subsets. That's what this notation is saying. In a picture, this is a run of the greedy algorithm for the function at time t, for the collection of sets in the system at time t. So in this picture, in the x-axis, the x-axis represents the elements of the ground set in the order selected by greedy, and the height of each of the vertical bars is the number of subsets it's newly covering given its position in the ordering. All right, so it's a representation of the greedy algorithm. Of course, at some point, the greedy algorithm will decide that it's covered everything, and so everything afterwards will have 0 marginal value. Okay, so this was the story at time t after we ran the greedy algorithm. At time t plus 1, a new subset arrives. Now, we've currently ordered our elements according to the greedy algorithm at the previous time step. The new greedy algorithm for this time step will come along and say, whoa, 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 please rearrange your solution completely. You've done this all wrong. And because you're too eager, you'll go ahead and you will completely rearrange your solution. Of course, you'll be competitive because you're running the greedy algorithm for the current time step, but you might pay way too much in the recourse. A better idea is to instead walk towards the greedy solution. What do I mean by that? We'll run an algorithm that maintains as its state a permutation pi on the ground set. So in our minds, our algorithm is maintaining a picture as in the last slide. And we'll think of this, this permutation pi as the stack trace or the history of some offline algorithm. Given such a permutation, this induces a solution for the hitting set problem, which is just the prefix of non-zero heights. All right. So the idea is going to be to perform local search on this permutation. Now, if we can argue two things, one, that when this local search terminates, this permutation corresponds to the stack trace or the history of a reasonable algorithm for the hitting set problem. And second, that this local search doesn't take too long. These are the two things we need to argue. Here's the local search. We consider two kinds of local search moves until none are available. The first is called a swap. So if we ever see a blue element followed by a taller red element, we swap them. This is a bubble, as in bubble sort. Now, when red cuts ahead of blue, it might steal some number of subsets from blue because red is now earlier in the permutation, and any subset that contains both red and blue will now be assigned to red. but the increase to red and the decrease to blue will be the same. The second type of local search move is called a jump. So an element is allowed to jump ahead in line, provided it meets the following criteria. When an element jumps ahead in line, it steals some number of subsets from each of the elements it jumps over, just as the red did when it got ahead of the blue. This element, the black element, for example, is allowed to jump ahead of red if the height of the black element after the move is at least, let's say, 100 times the heights of anyone that it cut over, anyone that it jumped over before the move. All right, so a few notes. Swaps cost 0 recourse. Why is this? Well, we only swap two things if they had non-zero marginal value, so they were already in our solution. Of course, if blue decreases to 0, it might leave the solution, but we said deletes are free. Okay. On the other hand, jumps are the operation that may cost us recourse, namely when the element jumping comes from the tail of the permutation with 0 height. Okay, on to the analysis. Let's argue about the competitive ratio first. I claim if no moves are available, the solution is 100 times log n plus 1 competitive. Suppose we have a situation where a red element is less than 100 times the best element we could have put in red's position. Meaning there was a blue element that if we moved it to red's position would be 100 times taller than red. Now, if our permutation is stable with respect to the local search moves, there are no swaps available, which means that the permutation is sorted in decreasing order. We've finished bubble sorting. And so not only is blue 100 times taller than red after the move, it will also be 100 times taller than anyone in between. But this means that blue moving ahead of red is a legal jump as we've defined it. And so this, to conclude, if there are no swaps and no jumps available, this situation cannot arise, which means on termination, this permutation pi has the property that every element is within 100 of the best element we could have put in that position, meaning it's the stack trace of an approximate greedy algorithm. Now, one can look through the proof of the analysis, the competitive ratio of the greedy algorithm, and you'll see that this fudge factor of 100 translates to an extra 100 in the competitive ratio, but no more. And so our bound is 100 times the bound given by the true greedy algorithm. That's it. So it remains to argue about recourse, and we'll do so with a potential function. We'll define a potential phi, and we'll argue a few things about it. Phi is greater or equal to 0. Phi does not increase when we perform swaps. Phi increases by at most some bounded amount when a subset arrives or leaves. And phi decreases by at least some amount during jumps. Why is this a good idea? Well, imagine that phi is energy in the system. Every time the world changes, we either get or we're either given or a new function, a new subset, or a subset departs, some amount of energy enters the system. Every time we pay recourse, we expend some amount of energy in the system. Any other operation that doesn't cost recourse only expends energy, and energy can't go below 0. And this will mean we can only expend energy so many times, meaning we can only pay so much recourse. So here's the potential function we use, this quantity that's the sum over I of VI. VI was the heights of the vertical bars in the histograms that we've been looking at. So VI is the number of new subsets covered by the element pi I in the permutation pi. Okay, and if we use this potential function, we will prove that the increase to the potential is at most 1 when a subset arrives or leaves, and the decrease to the potential is at least 1 during moves that cost recourse. And together, this will imply an average recourse bound of order 1. Divide this by this, and we get order 1. So just a note, this quantity here, one can call it different things, but one thing it is a special case of Salas entropy, which is a generalized parameterized family of entropies. It generalizes Shannon entropy. And in some sense, this makes sense that entropy is a good proxy for progress towards a competitive solution. Why is this? Well, at least in the unit cost version of this problem, a good solution is one that is sparse. And so it makes sense that entropy should be low at a competitive solution. So let's do the proof. I'll skip the proof of 1 because it's straightforward. So why does phi not increase with swaps? Well, suppose we perform a swap. Red cuts ahead of blue, and red and blue grow and shrink by the same amount. Well, the square root function is concave. And because the increase to red is the same as the decrease to blue, concavity precisely means that the contribution to the increase by red is less than the contribution to the decrease by blue. And so that's it for that claim. Why does phi increase by at most 1 when a subset arrives? Again, we're going to use concavity. So here's the change to the histogram when a subset arrives. Suppose it arrives and it's assigned to the element, the black element. The change in the potential is the following. Every element other than black does not contribute to the change in the potential. And so we're just looking at the contribution to the potential after minus contribution before of the black element. If its height before was k, this changes square root k plus 1 minus square root k. And it's easy to see by concavity that, again, this is less than 1. So it remains to prove the last point. And this is, in some sense, the most interesting part of the proof. So consider a jump. We'd like to show that the potential decreases by at least 1. Suppose some element u is jumping ahead in line. And for the purpose of simplicity, let's assume that u is coming from the tail of the permutation where all of the marginal values are 0. Let's define vi, as we did before, as the number of subsets owned by pi I, i.e. the vertical bars, in this before picture. So before u jumped over. Let's let ai be the number of subsets that u steals from pi I when it's jumping over. In other words, this hatched region over here. The change in the potential is phi final minus phi initial, which is this expression. So what is this? This first term is the contribution of u to the potential after the move. Why is this? Because u's height was initially 0. So after the move, its height is precisely everything it stole from everybody, which is the sum over I of ai. I's contribution, pi i's contribution to the potential after the move is its height after the move, which is its initial height minus what u stole. And its contribution before the move is just square root vi. So we need to bound this expression and ideally show that it's bounded above by -1. What we'll do is we'll bound the difference in these last two terms by the first order Taylor approximation. So we will take the Taylor approximation at vi, and concavity will let us conclude that this difference here is bounded above by the derivative at vi times the displacement towards vi minus ai. So the displacement here is negative ai. The derivative of square root vi is 1 over 2 square root of vi. And so we can bound these last two terms by minus ai over 2 square root vi. And we're just doing this coordinate by coordinate and summing over I. Now, it looks like we might have made negative progress here. I've introduced a sum with a strange ratio, but actually we're almost done. So recall that this move that we're performing is a valid jump, which means that the height of u after the move is at least 100 times the height of anyone it's jumping over. The height of u after the move requires precisely the sum over j of aj. So we get this bound. Now, vi appears here in the denominator. There's a negative sign. Two wrongs make a right, and we can use this inequality to go from here to here. Now what happens? Well, because we're summing over a different index j here, we can pull this summation outside into the numerator. We'll get a summation over I of ai in the numerator, square root summation over j of aj in the denominator. These cancel out. We collect terms, and this expression simplifies to -4 square root summation over I of ai. Because we're dealing with a hitting set problem, if u is jumping over, its height after the move is at least 1 because it's covering at least one subset. And so -4 square root summation over I of AI is indeed bounded above by -1. That's it for the proof. I'd like to just say a few takeaways. So our work simplifies previous work on dynamic low recourse covering problems and generalizes to a significantly wider range of problems. We introduce a new local search framework and a new potential function, the Salas entropy, in the context of dynamic algorithms, and we really hope that they find uses for other problems. There's several open questions outstanding. One is, can one remove this log term from the recourse bound? That's the tilde that I put over the O. Are there worst case as opposed to amortized recourse bounds that one can give? Can this framework be used for other problems in dynamic algorithms? And finally, is there a reasonable update time variant to consider? So in our work, we basically only think about recourse, and we've ignored the question of update time, although as written, all the algorithms in our paper are at polynomial time. Thanks, and please reach out with any questions or ideas for future work.